On example 1, how could local linearity help evaluate the limit as x approaches 0 of sine x over x? Man, why does this function keep coming up? This specific limit. I don't know, there's probably a good reason. So if you remember, local linearity was about the idea that when you zoom in on a graph super close, it starts to look more and more like a line, right? And that was our opening activity, this picture that's from it, where the function sine x looks like y equals x really close to the origin. So if I am trying to evaluate the limit as x approaches 0 of sine x over x, remember that from our activity, sine x right there looked just like y equals x. So let me approximate sine x by x really close to the origin. And why can I do that? Because that's the only place this limit is happening. It's only happening around the origin. So I'm going to say that this thing can be approximated by, bear with me, the limit as x approaches 0 of just x over x. Hey, what's x divided by x? Don't worry about the fact that there's an x on the bottom. This is not telling me, like this limit is not telling me to directly evaluate this new function at 0. It's seeing what it is approaching. What's it getting closer and closer to? So I could go ahead and cancel these things out. X divided by x, pretty sure that's equal to 1. Now, in a future lesson, we will learn about this thing called L'Hopital's rule, or L'Hospital's rule, in which what we do when we have this indeterminate form 0 over 0, which is what happens if we stick a 0 in for x there, of course, then what you do is you take the slopes. What does it look like the slope here at the origin was for sine x? It was a 1. And then what's the slope of x? It's also a 1. 1 divided by 1? It's 1. Just a preview of what's to come with L'Hopital's rule. Okay, so let's go back and look at example 2. The domain of the rational function f of x is equal to x cubed minus 1 over x minus 1 excludes x equals 1. Of course it does. If we stick 1 in the denominator there, it makes it 0. I've just divided by 0. So numerically and graphically estimate the limit as x approaches 1 of that particular function. So you may have had something like this way back in Algebra 2 when you were first learning to graph asymptotes and stuff with those rational functions. Apparently it's time to go to the next class. Yeah, and so when a number was excluded from the domain, what happened there? Did you have yourself an asymptote or did you have yourself a hole, right? That was something that you had to consider, and that's the question that this limit is trying to answer here. All right, so let's first tackle this graphically. It's a piece of cake. I just pull out my graphing calculator and I type that thing in, assuming I can remember what the heck that function was. So it's y equals, in parentheses, x cubed, arrow out of that, minus 1, arrow out of that 2, divided by, more parentheses, x minus 1. X plus a negative 1? All right, that works. Are you sure it works? Because I got a parabola and I was expecting something weird. Notice that this thing does not have an asymptote. Instead, what it has is a hole, right? And like I can try to zoom in. I'm trying to look at around x equals 1. Try to zoom in there. And at x equals 1, if I follow that up, it looks like it hits right there at 3, right? Of course, it's not defined at 3. I can try as hard as I want to zoom in. I'd never ever see that speck that's missing because this graphing calculator is doing a really, really good job. It's just a speck, a tiny, one tiny little thing that's being taken out of that graph. On your TI-84 calculator, though, it doesn't have quite the resolution that Decimals does, and so you will see a little tiny hole in your graph. So what does it look like the value of this limit is approaching? Come back over here, and I'm going to say something like this, that it seems to be approaching 3. I want to put that approximately equal sign until I get to the point where I can actually prove that it's 3. And we'll learn to do that in the next lesson on how to analytically derive the value of a limit. But right now, we're just estimating them. The other way that we can estimate them is numerically. And numerically, I'm going to look at a table of values, and I want to populate the table myself. I don't want it to auto-generate. And so let's kind of build a table here of what that would look like. So I have a regular good old-fashioned T-chart with X and Y values. And right in the middle, I want the value that I am looking for, which is 1. And then our calculator should give us maybe some kind of error because it's undefined at that particular point. But we want to know what's happening over here and over here. Sure, that one's undefined. Maybe there's a hole, maybe something else weird's happening, but is it approaching a particular thing? So on my X values, I'm going to step away from 1 on the right side, bigger than that. So this is where we start. And then here we're going to get a little bit bigger. And on the other side, on the left side, thinking of a number line, I'm going to get a little bit smaller than 1 by the same increments. And we're going to build this so this table is symmetric so that it's really easy to see some sort of pattern in the f of x values. Okay, so what is something that is just a teensy bit bigger than 1? How about 1.001? All right, now I'm going to step away by just a little bit more. How about something like 1.01? And step away by just a little bit more here. I have 1.1. And then, of course, we'll have our calculator auto-populate what these function values are supposed to be. Now, I want to keep this kind of thing symmetric on this side. I essentially added 0.001 to get this value. I'm going to subtract 0.001 to get the one on the small side. So it's 0.999. And then keep going, the same exact pattern, 0.99. And then one more, 0.9. And then hopefully that's enough of a picture to establish some sort of pattern that will give us some evidence that this thing is approaching. Like this should be a 3 right in there. So let's take a look. I think I can do this on Desmos. So on Desmos, you hit the little gear here, and then we can turn this thing into a table with that little button. All right, and it auto-generates numbers. Your calculator will do the same thing. So on your calculator, you want to go to Table Set, and in Table Set, you are going to choose for your independent variables, your x's, to ask. And for your dependent, you want that to be auto. So you should be able to switch those, and then you can plug in any values that you want, and that's exactly what we're going to do here. So instead of that -2, that's not what I want. I want 0.9. Let's hit return. And then I want 0.99. 0.999. And here's where I want 1, and it should give me something that's undefined. And now start building something that's a little bit bigger than that. 1.001, 1.01, and 1.1. And that should be enough. And so now look at the table that we have here. It seems pretty clear that as we approach 1 from either side, the y values are approaching 3. So it's more evidence to suggest that our limit value is 3. So again, I'm going to say that this, hey, this is what I want, that this still seems to be true. So back here in the slideshow, I have both of these things in pictures. So here is that table of values that demonstrates that both from the bottom and from the top, bigger and smaller than 1, it seems to be approaching 3. And here on this graph, I can't even see the hole. I actually had to physically put the little open circle dot so that you can visualize where that thing would be. Okay, and this one was not an asymptote. That's what the limit was able to answer for me. This function is approaching 3 as x approaches 1 from either side of it. So it's important to understand, super important to understand that if f of a is not defined for some function, so in this case, f of 1 was not defined, that did not prevent the limit from existing at that particular point. It was still, the function seemed to be approaching 3. All right, in the next video, I'm going to show you, just kind of give you a preview of how we could have and how you may have found the value of that limit last year or the year before that analytically, okay?